Welcome back, OChem. Let's continue our radical halogenation. This is where we left off in the last video. Remember, we did our radical halogenation with chlorine, and we ended up with an initiation, propagation, and termination step, and we made alkyl halides. Now, this reaction works with both bromine and chlorine. And then, so let's go ahead and draw the product for bromine, and then we're going to stop and compare the two processes. So let's give you the general for bromine. Let's take our propane. We're going to use bromine, elemental bromine, and light. Elemental bromine is a liquid. There are only two natural elements that are liquids, mercury and bromine. Bromine is one of them. And it's actually a creepy red liquid. It just reminds me of Halloween. It's got a nice red vapor always with it. But it's an old school test. We're going to see bromine again with our alkenes. You can always tell when these reactions are working. They're very visual. If you've got bromine present, it's red. When you use up your bromine and you break that bond, it is now colorless. Okay, so where did our bromine go? Well, we have two options for products, just like with chlorine. But wait, there's a cliffhanger. This is so much fun. Let's scroll up here with our chlorine. When we make our chlorine products, we end up making one-to-one both of them. Shut the front door. That kind of makes sense, maybe, right? We're going to come back and explain that in just a second. But with our bromine, what's your gut tell you? Do we make one-to-one? No, or I wouldn't make a big deal out of it. In fact, we make over 99% this one. And way less than 1% for this one. So in fact, we're going to use bromine an awful lot in synthesis because we're going to get one product, not two. So let's draw the mechanism for bromine, and then let's come back and try to explain why we might get a difference in those two products. All right, let's draw our mechanism, and it's going to look an awful lot like the chlorine mechanism, and it should, because our radical reactions tend to look the same. We have an initiation. So take your bromine and light, and let's break that bond. Single arrows, remember? So you're going to make two bromine radicals. Just like the last process, we're going to use both of them. Bromine radical number 1 is going to do a hydrogen abstraction. Okay, now this is where it gets fun. So you need to choose wisely. If you're about to make this product 99% of the time, then that means that this is the hydrogen that we're going to abstract. So let's keep track of our electrons. We've got 1 electron from bromine, 1 electron from hydrogen. We need to leave behind 1. So we just made HBr. Okay, just like our HCl, and we left behind our radical on our propane. Okay, I love it. So now, once we've got that propane radical, let's continue our mechanism down here. Oop, wrong pen. We've got our radical right here. And then what is left over? Well, we've got bromine radical number 2. So let's terminate that reaction, and let's make that alkyl bromide. Okay, let's add in our vocab. Here is our initiation, here is our propagation, and here is our termination. I love it. Okay, now let's line those up next to each other, and let's see if we can't explain why in the world they would be different. So let's just give an example. Chlorine. Remember, we are going to have both of these products formed in a one-to-one mixture. And in bromine, holy cow, we really just make this one. Okay, so we've got a couple of major differences between bromine and chlorine. First of all, let's look at our initiation step. With our chlorine, that first initiation step, let's compare it. That's their first difference, right? You're initiating using a different element. So our chlorine-chlorine bond is worth 58 kilojoules. Our bromine-bromine bond is worth 46 kilojoules. Okay, so which one's easier to break? Bromine is easier to break. Okay, well, why would that matter? Well, if that bond is easier to break, then let's take a leap forward and say, well, that means that this radical then is more stable. All right, so if chlorine is harder to break, then this radical is less stable. So if it's, let's take one more leap, wait with me here. If that radical for chlorine is less stable, that means it's more reactive. That means our bromine is a little less reactive. Okay, so that's the first part of the puzzle. These radicals are actually different. If chlorine is more reactive, it is less choosy. In other words, it is going to form a bond to the first thing it smacks into. These reactions are collisions. So whatever hydrogen that chlorine radical smacks into, that's the product you're going to make. That's why you have a mixture. And whenever you use chlorine in any kind of alkane, you're going to have a mixture of all of those possible products because chlorine is literally just loosey-goosey. It is less choosy or less selective. It is more reactive. All right, but then bromine is a little bit less reactive, so it can be more choosy or more selective. But you're wondering, wait, Dr. A, why? What is it choosing? There's two pieces to the puzzle. Here's number one, the reactivity between your chlorine and bromine. Here's number two, in our actual radical that we form, isn't that different as well? Yes. So is there a difference between the hydrogens that you take in order to make this radical? Yes. In fact, we're going to call this radical stability. And we'll use this all semester. In fact, it would be similar to our carbocation stability. So let's make a little chart. The most substituted, the most better. Okay, that's awesome. Not an English class. So our tertiary radicals, if we can form them, are actually the most stable. Secondary, primary come way behind. So if we were going to compare these, we've got a nice secondary radical or a primary radical. Which one wins? Your secondary radical. So look at what bromine selects. It selects the most stable radical. So if you have an option in your reaction to form a tertiary radical with bromine, that's exactly what you're going to form. So let's give an example. What if we have a nice ring like this? Let's compare. What would you get with bromine and light? Let's draw the right structure. Where would your bromine end up? Hit pause if you want to try it for yourself for a second. What is the most stable radical you could form out of this whole compound? That's going to be right there, tertiary. So what's the product you're going to form with bromine? This one. Now let's compare to the products you would form if you did this reaction with chlorine. Oh my gosh, you know exactly where we're headed on our next take-home test, don't you? Draw all possible stereoisomers of the following reaction. I know, right? Doesn't that sound fun? Let's start with the constitutional isomers. Chlorine can go everywhere. So how many different products can we make? Let's draw them. Isn't that fun? You can make all of those. I love it. And then of course, just wait for it before we end the video. Let's end on a cliffhanger. Let's end on a fun note. Do you have any stereo centers in here? Oh, doesn't that make OChem so much fun? Yeah, it does. And then doesn't this resemble our take-home question from the last unit? Well, which ones are stereo centers? Which ones aren't? Do you have any symmetry? Do you have meso? Do you have cis or trans? All of those questions are valid here. Okay, so let's kind of leave that as a cliffhanger. Do we have meso? Do we have cis or trans? Oh my gosh, how fun. Let me leave one last hint. All radical reactions go through a planar intermediate. That means that this radical is flat. Why do you care? You care because that means the bromine radical is going to come in on either side 50-50. Do you remember our terms from last unit? What does it mean if you make both products 50-50? These are reciprocal.